The theorem we want to discuss today concerns the partial sum of the Fourier-Haar series of functions from L1. So, first, some preliminary notations. We know that for the nth Haar function, chi n, it is true that chi n at x equals zero if x is does not belong to the closure of the dyadic interval delta n equals delta ki, and it is I minus 1 over 2k, I over 2k. And chi n x we take to be equal to 2k over 2 if x is in the left half of the dyadic interval, and it is negative 2 raised to the power k over 2 if x belongs to the right half of the dyadic interval. Also, so the theorem states that also we prove the theorem first. We first prove the theorem for the case n equals to 2k, and then we prove something more general for any index n. Now, the partial sum, nth partial sum, is defined as the following finite sum and we want to see that it equals 2 raised to power k integral over delta ki ft dt, where delta ki is the unique dyadic interval out of delta k1, delta k to 2k, which contains x. So now to prove the theorem, also let me put here the expression for the nth Haar coefficient, Fourier-Haar coefficient in the Fourier-Haar series of f. CNF is defined to be the integral from 0 to 1 of f t chi n t dt. Now, the proof. First, introduce the function mkfx, and we want it to be equal this expression here. From its form, again, let's recall once again that delta ki is the unique dyadic interval which contains x. So from the form of mk, it's obvious that mk is constant on each of these dyadic intervals, and the first n, where is our n here? N Haar functions as well are constant on each of these dyadic intervals. This follows from the form of the Haar function. And then we conclude that mk can be introduced as a linear combination of the first n Haar functions. Therefore, we write down for mk this formula here. Now, this means that to prove the theorem, we only need to see that Aj equals Cjf. We will see this in two steps. First, this is almost obvious. but let's see the details nevertheless. So, and the second. First, CJMK is integral from 0 to 1 mkfx chi jx dx. If we substitute this sum for mk, then the summation comes in from j changes from 1 to j is in fact already used, so let's have something such as n here. N changes from 1 to n, and then a n comes in front because it does not depend on x, and then we have the integral here from 0 to 1, and chi n x, this chi n x here, then our chi jx and dx. Because the Haar system is an orthonormal system, so we know that if n equals j, then this integral is 1. If n does not equal to j, then it is 0. Therefore, the value for this expression is exactly a j. Only we have the summand, which corresponds to the index small n equal to j. So we have the first claim done. Now let's see the second one. Let's we don't need any more this part here. This as well. So CJMK is integral from 0, 1 mkfx times chi j x dx. This integral we will put as a sum of integrals over the dyadics. As a next step, we will notice that each chi j is constant on each of these dyadic intervals. Therefore, it takes the value which it takes. In fact, so here we need to use another summation index because we have already j here. So let's correct this thing here. Let's take n here. So we know that each chi j is constant on each of these dyadic intervals. Their number is 2k, and the value it takes on each of them is equal to the value which in particular it takes on the at the midpoint of each of them. Therefore, I can put this expression as as such. In fact, okay, let's keep these expressions here. So now we take a look at mkfx. This x is the integration variable, therefore it belongs to this delta kn, and hence in the expression for mkfx, this delta ki will be the same as this delta kn. And then we will have some n changes from 1 to n, the constant value of kj, integral delta nk here, 2 to k, integral over the same delta kn, and then ft dt as well as dx. I think we can erase this part as well. So sum becomes 2 to k negative 2 to minus k, the length of delta nk cancels this 2k here, and this integral does not depend on x, therefore it comes out of the integral in front. Therefore, now we have this expression here. Chi j goes back because chi j is this chi j at the midpoint is the constant value of chi j on each of these delta k n's. Therefore, it goes inside the integral, goes back inside the integral, and from 1 to n, integral delta kn here, chi j t f t dt. This is exactly integral from 0 1 chi j t f t dt, but this is the definition for CJF. Therefore, we started from CJMK, and good that it is equal to CJF. This second claim holds as well. Therefore, the theorem holds.